Good afternoon, everyone. My name is Robbie Meehan. I am a geologist who I'm lucky enough to complete a lot of my work with and for Geological Survey Ireland, particularly groundwater section. And I'm delighted to be speaking here at the conference today to have been invited by IAH. And I'm going to talk about a recently, I suppose, begun project whereby GSI are looking at a regional assessment of groundwater resources. I'm going to talk in particular about a case study from the Boyne catchment, and I'm going to focus on the limestones particularly, especially bearing in mind the theme of the conference. And I have to thank at the outset my fellow authors that are listed here on the screen, particularly Katie Ted, who has done the lion's share of the actual work and analysis on the Boyne catchment for this presentation. So where are we? The Boyne itself, it's located just northwest of Dublin. You can see there in the top left, the map of Ireland. It's in Northeast Ireland. It's a lowland catchment. There are obviously a few higher hills, but still relatively low hills around the edges that feed the tributaries down to the main channel. The main channel runs from where it says County Offaly there at the bottom left, right up to Drogheda in the top right. The Boyne River itself flows from southwest to northeast, and its main tributary is the Blackwater there in the north central portion of the catchment. So the Boyne itself, it's noted and it's notable. It's quite famous in a sense owing to its archaeology and history. In a heritage sense, it's a very famous catchment and valley in itself. And looking at, I suppose, some of the sites there moving from the top left around clockwise, you've got Dunmow Castle, you've got Newgrange, you've got Bective Abbey, you've got Trim, you've got various monuments which have since even disappeared, some of them in the Bend of the Boyne area around Newgrange itself, and you've got Kieran's Well there in the bottom left, which is quite a famous holy well. And underpinning all of those, it may not be apparent at first glance, but limestone is so important. Trim Castle there, you can see, is built directly on top of the limestone. Most of the monuments are built from limestone itself. If you even start looking at the old cemeteries in the catchment, you can see there in the center, many of the tombstones are actually created and etched out of limestone. And you can see how the limestone is being, in a sense, karstified there in the central image. So limestone is important under the Boyne, and I will mention that particularly towards the end of the talk when I start to synthesize the results and the outputs of our study. So first question is, why is GSI looking at a regional assessment of groundwater resources? I suppose the main point of this slide is that there has been obviously a lot of media coverage about climate in the last few years. We have had a number of droughts, we've had a number of severe climatic events, but the work that we're doing is not a reaction to those events at all. It's not a reactive study, it's actually a proactive study. And a couple of years ago, GSI were approached by Irish Water to start to investigate the long-term sustainability of groundwater resources throughout the country. So this is how the project was engendered, and the main aims are to prioritize further investigation into groundwater resources, to improve our hydrogeological understanding of the catchments within the resources via conceptual models and water balances, and to identify information gaps. So if you look at a history of groundwater resource management in Ireland, this isn't the first time something like this has been done. And this might not be readily apparent when you start looking at the literature, but there have been a number of studies completed at a regional or national scale. The Northeast Regional Development Association, or NERDO, in the early 70s begun a 10-year project. NERDO itself is an amalgamation of the county councils of Louth, Monaghan and Cavan and Forres Forbaha. And they went out and collected data on the ground. They did completed well surveys. There was a limited drilling program, but a very comprehensive tree volume report was produced, and a number of viable water supplies were provided, and a number of those are still in use to the present day. In the late 70s, then GSI they undertook a project for, at that time, the European Commission, as it was called, and they calculated the national groundwater resource. And that was principally driven by the estimation of recharge. At that time, most of the maps were relatively, I suppose, small scale in terms of the hydrogeology of the country, which is very different to the situation that we find ourselves in now when we actually start to look at what's available. Eugene Daly and Associates in the late 2000s studied the Dublin region and looked at the potential for the large-scale development and abstraction of groundwater to contribute to the water supply requirements of the capital. And on the back of that, then Jacobs-Tobin in 2015 completed a source yield review for the Eastern and Midlands Regional Water Supply Project, examining groundwater specifically. As well as that, there's been a number of specific engineering and hydrogeological projects looking at water balance studies, and I've just listed a couple of them there. And I suppose the model and the maps that we would be most used to as hydrogeologists in this country that look at groundwater resources across the country are the GSI National Aquifer Map and the National Recharge Map, which were produced in the late 1990s and early 2000s, and which most of us would refer to in most studies. The project that we're working on now, the idea is to compile all relevant, readily available hydrogeological information for the catchments that we're looking at, develop an initial hydrogeological conceptual model for them, provide a basis for prioritizing further investigation into groundwater resources, and that happens at sub-catchment scale really. Identify existing information which is not available for these reports, but which would be useful for further analysis. That's stuff that's there now that we just can't get our hands on. And also identify information gaps which could be addressed by GSI or other parties. And it'll initially comprise 32 catchment reports and then rolled out for the rest of the country. So these are the catchments that we're looking at. You can see the Boyne there in the top center. But the reason we're looking at water catchments and surface water catchments in this study is that they're the internationally recognized management unit really for water resources. And when you look at surface water catchments, we have a calibration point for all water in that catchment. We know how much goes in via rainfall and how much leaves to the sea. And from that, we can start to estimate and pretty well estimate the amount, the proportion that's actually groundwater. If you were to use groundwater bodies as a management unit, you don't have a calibration point, and there's no inherent link between surface water and groundwater at the groundwater body scale. And I suppose, to my mind as hydrogeologists, we need to be starting to move away as well from just looking at groundwater. Catchment science is really where it's at nowadays, and you need a holistic view looking at groundwater and surface water together. In order to try and better appropriate, I suppose, and examine environmental issues, and particularly that is so useful when it comes to things like climate change and the biodiversity crisis that we have currently also. So how is this different to the GSI's aquifer map, for instance, or even the recharge map? Both can be used as groundwater resource beginning points, I suppose. The idea is that we examine all relevant and available regional scale mapping to develop a conceptual understanding, like I mentioned there a couple of minutes ago. Use relevant site-specific monitoring data, which is at a more local scale, and use the conceptual understanding to divide the catchment into different hydrogeological zones. And that will then allow an assessment to prioritize areas for further investigation into the development of future groundwater resources, and importantly, to identify potential constraints. And that will become apparent as I move through the methodology and the thought process over the next 10 minutes or so. So the structure of the reports there's 4 parts to the reports and to the studies: the overview from regional mapping, the analysis of available site-specific monitoring data, the assessment of potential groundwater resources, and then the potential constraints. And I won't go into those in detail, you can read them there yourselves. But what you're doing is you're looking at a regional scale, I suppose, the overall pattern of hydrogeological elements within the catchments. You're then using site-specific monitoring data to better understand what's happening. And you can then derive a conceptual model based on that for the various subcatchments and emerge with hydrogeological zones, and then examine your potential constraints. What areas might you not go into because of other issues such as Water Framework Directive status or European sites protected areas or whatever the case may be. So the first element to the study, to the empirical study, is rainfall. And we have daily rainfall data from all local rainfall stations, and they're used to calculate the average annual rainfall within the catchment. And we derive standardized precipitation index graphs. And these basically characterize the meteorological drought element at a range of scales. And these are used to provide periods of above or below average rainfall within the catchments themselves. We can then look at daily potential evapotranspiration data from synoptic stations and then calculate the range of outflows we'd expect from the catchments, and that can then be compared with hydrometric data. With regard to surface water, again, as hydrogeologists, you may not think that surface water might be important, but it's critical when it comes to this catchment analysis. OPW, EPA, local authorities, ESB, we all know that all of these bodies monitor surface levels and flows, and we know that there's a vast amount of hydrometric data available at different locations throughout the country. And flow statistics from this hydrometric data can be compared then to the calculated Q95s from the EPA hydrometric data. So the first thing that we try and do is hydrograph separation. We try and separate out the base flow from the surface water flow. And we use flow duration curves. These are a cumulative frequency curve that shows the percent of time specified discharges are equaled or exceeded during a given period. And on the chart here, we can see flow duration curves, which are ordered by stage, and they're showing per kilometer squared the actual flow duration within the different tributaries and the different channels within the catchment. The thick lines refer to the main Boyne channel, and the thin lines are the tributaries. So the graph shows a kind of a comparison between the mean hydrometric flows at hydrometric stations with relevant available data and the estimated flows we've calculated using the effective recharging area. So if you look at, for instance, Slane Castle there, which is the dark, thick line in the central portion of the graph, the mean flow there is just over 35 cubic meters per second. That's lower than the calculated estimated mean flow of 37 to 39 meters cubed a second. And that would probably reflect an element of groundwater storage. Like in that stretch, just upstream of Slane Castle, between Navan and Slane, you've got wide, deep terraces of glacial fluvial sands and gravels. You'd expect there to be a significant groundwater component there, which is why you'd expect that there's a sort of a decoupling between the expected flows and the calculated flows. Looking at a different scenario, the two lower graphs there, which refer to the Rosehill, Minolty and the Deal Raharney tributaries, those match really well with the estimated calculated flows. And those catchments, those subcatchments, are more surface water dominated. We've got lots of moderate and low permeability till, very little sand and gravel, if any, and lots of peat. So the flow duration curves, they're used to describe how the flow changes as you move downstream, and you can start to separate out the base flow from the surface water flow. If you've no hydrometric stations in the catchment, what we do is we use the EPA's cube model. And I should mention that we, along, I suppose, all stages of these studies, we're working quite closely with the EPA. They're not only providing data, but they're actually working with us and reviewing our outputs and making sure that everything, I suppose, tallies in order to give the best result possible and the most comprehensive report possible at the end of the day. With regard to groundwater levels, obviously groundwater hydrographs, they're direct evidence of what the aquifer is actually doing. And to interpret the hydrographs, you can analyze rainfall, and I mentioned the SBIs earlier on. So you can start to look at what's happening with regard to water levels in the boreholes and with regard to the rainfall itself. So if you look at Dunshaughlin there on the right-hand side in the Boyne, you can see that there's a pretty good correlation between the rainfall amounts, which is in the lower graph there, and the hydrograph, the actual groundwater levels within the borehole. Just outside the catchment, we've got a borehole at Kiltrough, and we can see that there has been a downward trend over time with regard to the groundwater levels there. It's recovered slightly in the last couple of years, but that may be due to less abstraction at the actual locality itself. But that's what you'd expect given what we've seen in the regional assessment, because that area is overlain by thick, low permeability tills. There's minimal recharge. And even though you've got a karstified bedrock aquifer, you may have issues in the long-term abstraction in those sort of scenarios. With regard to hydrochemistry, GSI has recently been processing reams of groundwater hydrochemistry data. And that was collected through the years across various geological terrain. Again, we're using lots of EPA information from the groundwater monitoring network to look at this. And we can output Piper charts like we have there on the left-hand side, and the Boyne monitoring stations are those in the blue X's. So you can compare it to what's happening elsewhere hydrochemically in the country, and you can start to look at the hydrochemical signature. And what we've seen is that the Boyne calc has problems, and this has long been known, I suppose, anecdotally, but there are issues with regard to iron, with regard to manganese, with regard to hydrogen sulfide, and more. Even close to the mine in Navan, you have issues with regard to copper, very elevated copper levels, barium, and other, I suppose, rarer elements cropping up at high levels within the groundwater. We also then, towards the end of the empirical study, look at potential constraints. I mentioned this earlier. And we've looked at hydrogeological constraints with regard to the aquifer types and the recharge amounts. Existing abstractions are looked at, and we also examine protected areas in ecology and the impact we may have on those. But as well as that, we consider sustainable abstraction using water framework directive limits as guidelines. So we're actually just following the methodology that the EPA have derived to establish groundwater threshold values there. And as well as that, we complete surface water capacity tests, and those are proven quite useful, for particularly with regard to the sand and gravel groundwater bodies. A water balances assessment is estimated for each catchment. So you're just talking about plugging all of the information, all of the calculated empirical values into an Excel spreadsheet. You're assuming steady state conditions, but that gives us an idea how much potential error we may have, and we then re-examine and go back, and as you would in most natural science, you're trying to undermine your model and make sure that everything tallies as best as possible and that there's as little error as possible with regard to all the various elements. And there are lots of different inputs and outputs with regard to the water balance. All of these are included: effective rainfall, surface water runoff, groundwater recharge, imports from other catchments and surface waters, inflows from other catchments through groundwater, anthropogenic discharges, surface water discharges to groundwater, and groundwater discharges to surface water, so losing streams, seeps and springs and so on, and outflows to other aquifers of groundwater, surface water and groundwater abstractions and surface water inputs. So in the end then, how do we derive our output resource maps? So the starting point, as I mentioned earlier, is really the aquifer map and the recharge map there shown. You then are starting to conceptualize hydrogeologically what's happening within the various subcatchments within the overall catchment itself. And you're trying to look at how much is being evapotranspired, how much is available as groundwater, and how much is actually flowing off as surface water within the area you're looking at. And with the Boyne, what that means is you end up with 5 zones. You have the northern zone, which is surface water dominated, relatively poorly productive aquifers, only 14% of the effective rainfall recharge into groundwater. On the southwest there, you also have a surface water dominated catchments with slightly more effective rainfall recharging, 27%. And the Drogheda zone on the right hand side there over at the east, even though that's underlain by, in the majority, regionally important aquifer, there's only 23% of effective rainfall recharging because of the thick, low permeability subsoil. So of the 5 zones, only 2 are groundwater dominated. The Castle Pollard zone, which is that locally important karstified aquifer in the northwest, which has 47% of the effective rainfall recharging, and the southeastern zone, which has between 41 and 72% of effective rainfall recharging. Again, that's a groundwater dominated zone. So initially, they're the 2 zones that you'd hope to start looking at in a bit more detail. When you then look at the zones and what they mean on top of the aquifer map, you can immediately, I suppose, discount the 3 zones where surface water dominates and where there's very little recharge. What you're left with then is your southeastern zone, where we've got the calc limestone, which is locally important, and we've got a number of sand and gravel bodies, and we have the karstified area at the northwest of the catchment, up near Castle Pollard and Oldcastle. You can then take out these little inliers, you can see that, of the locally important and poor aquifers in that southeast zone. And around Navan itself, where Tara Mines is dewatering at a local level quite a significant area, and where there are water quality issues associated with newly mapped faults, mapped as part of the mine investigation, you can take out another area. And then the area up at the northwest, which is locally important karstified bedrock, about a third of that is actually SAC, the area there that's outlined in purple. Loch Bain, Loch Lane, and White Lochs and Ben Lochs, SACs. And as well as that, there are 2 fairly significant public water supplies taken over 11 megalitres a day from surface water in that zone. So that zone also goes. When you look at the calc then and what's left, the calc has issues with regard to the water quality. So that means that what we're left with is, when you examine the areas that have iron at a high level, it pervades the calc itself. So you'd kind of have a red flag warning sign where the calc is situated. So in effect, in the entirety of the Boyne catchment, what you're left with is some sand and gravel bodies, locally important sand and gravel aquifers, that could give you collectively maybe 12 to 15 megalitres a day, and a significant amount more from the calc, but with associated water quality issues. And that means that a cost-benefit analysis would be, I think, required if you were to start examining the abstraction of groundwater from that calc. What this means overall about limestones is, just because a limestone is a regionally important or locally important aquifer, it doesn't mean to say that it will have available recharge. Extensive current abstractions from the limestones may limit the amount of water available, regardless of what might be considered a sustainable yield at that point locality. So what we're trying to do with these maps is, I suppose, illustrate not just where there's lots of water, but where there's water it's viable to abstract. It's exploitable water, and exploitable in a sustainable sense. And that actually reflects back on the talk that Catherine gave earlier as well, I think. As many of our SSEs, SPAs, and NHAs, their European sites are limestone related, there may be significant issues owing to future abstraction of water in these areas. And another thing that this means about limestones is, many of our dirty limestones are really dirty. And hydrochemically, that means potential problems when it comes to abstraction at potential high costs. Overall, thorough catchment scale groundwater resources assessment, though, may mean that on a regional level, we can see the local areas have particular characteristics and potential issues. And I think that that's what the power of these studies is, that you can actually start to hone in on potential problems, and you can actually better understand areas that are having problems at the moment. And we've known, for instance, at Bog of the Ring, that some of the water supplies down near Gorey, that Tridabnit and Monaghan, which are all abstracting from really important karstowite aquifers, that they're overlain by thick, low permeability material that means minimal recharge, and that means that you're mining groundwater at an unsustainable level long term. And we'd be hoping that with these sort of studies, as we roll them out over the country, that we're going to arrive at, I think, a better and more sustainable future for groundwater resource management in the country. So I'd like to thank you very much for your attention, and hopefully we have some questions maybe later on about this. Thank you.